Hello.
So my name is Raja Ayyanar. I'm the chair for the power group at ASU, and today I'm going to talk briefly about our power program, go through the courses that we offer, introduce some of the faculty, and very brief overview of some of the research that we do. So thanks for coming. I know it's probably the midterm season, I think, right? So appreciate your interest. Okay, so probably you are aware that ASU has one of the, if not the largest, I'm sure among the top 3 at least, top power programs in the country. So that includes everything to do with power, transmission, distribution, power quality, power electronics, machines, things that I work on, everything included. So as you will see in the next slide, there are 15 faculty, core power systems, power electronics faculty in the group. That makes us, I think, probably the biggest group. And in terms of graduate students also, we have about 150 graduate students. So it's not just the numbers, in terms of the quality of the program, research, as well as education. You will see that we cover almost everything that is related to power engineering in terms of research. And not just theoretical research, we have good experimental lab facilities in which we conduct this research. So in terms of research excellence as measured by like the membership in prestigious academies, so we have 3 members of National Academy of Engineering. That's the highest honor an engineer or engineering professor can get in this country. So it's very rare that one single program has 3 NAE members. We also have several IEEE fellows and so on. So the feedback that we get from the employers of our students has been phenomenal. They always say that we need more of this student, that student. So we get great positive feedback from our employers about the students who go through our program and end up joining them. So I have one separate slide on the employment opportunities, but it's something that I want to emphasize. There is tremendous employment opportunities in this area. We'll talk about the reasons in a later slide. Okay, so that's our group, 15 faculty members. Go through them individually. I work in power electronics, switch mode, high frequency power electronics, and more recently focusing on solar PV inverters and power electronics for electric vehicles. That's my research area. Professor Hedman, he works in energy economics, energy markets, and he's an expert in optimization as applied to power systems. He now has a joint appointment with Department of Energy's ARPA-E program. He's a program director. And I think last year he won a very prestigious presidential award for early faculty members. Professor Haidt, I think he is retiring this semester. He is continuing as a professor emeritus. He is one of the 3 National Academy of Engineering members that I mentioned. His areas, he's an expert in distribution engineering as well as power quality. Okay? He is internationally well known for his work in those 2 areas. Professor Holbert is a nuclear engineer. He teaches courses on nuclear engineering related to power generation, and he also runs the certificate program for graduate students in nuclear power engineering. Dr. Karadi, his expertise is in high voltage engineering. Professor Moise Hedman, she's our own graduate. I think she graduated last year and then immediately joined as a faculty. She was a student of Professor Whitall, and they both work in bulk transmission systems, looking at ways to prevent blackouts, cascaded blackout events, and so on. Professor Chin Lei, she is in power electronics, slightly different focus than mine. She works in high voltage, high power electronics, things like HVDC that you may have heard of. That's her area. Professor Anamitra Paul, he may have seen him already in 360. He joined maybe a couple of years now from Virginia Tech, and his area is in applying wide area measurements for improved performance stability of power grid. You may have heard of phasor measurement units. PMU gives you much more insight on what is going on in power systems. His work is related to using them for grid improvement. Dr. Chen, also another power electronics faculty, high voltage, high power focus. Dr. Shankar, she works on cybersecurity and privacy as applied to power systems. Dr. Tylowski, I don't know if you can really see it. Dr. Tylowski, he works on computational methods, power flow methods as applied to analyzing bulk power systems. Professor Andrel, he worked at GE for a long time. Some of the widely used power flow software, both in the industry as well as in many of our courses, they were actually written by him. So he is very well known. He is also one of the 3 NAE members. Professor Vittal, he is the director of a big center that we are all part of. It's called PCIRC. His area is in power system dynamics, stability and control. He's also an NAE member. Dr. Wang recently joined us from Stanford. He is an expert in machine learning. He wants to apply machine learning and artificial intelligence to the problems in power systems. Dr. Meng Wu, she is from Texas A&M, again joined last year. She is looking at improved ways of integrating renewables into the grid. So that's the faculty in this area. Okay, so this is a slide that I mentioned. The reason why there is, I claim that we have tremendous employment opportunities in this area is over the previous decade, for a long time, the infrastructure development in the power area has not been up to what it was really needed. It was So because of that, we have a large need for new infrastructure development. So if you look at most of the utility equipment, say transformers or circuit breakers or big transmission lines, those are 40, 50 or even 40 or 50 years older, or even older than that. So obviously they need to be redesigned, replaced fairly soon. Add to that the emerging requirement on more environmentally friendly generation, renewable resources, distributed generation. So they require new type of infrastructure, right? So wind flows not close to your load centers, so they need to be transmitted through new transmission systems, high voltage transmission systems, so infrastructure for that. A lot of PV power plants, wind power plants, they need different types of infrastructure. So all of them have to be newly built. So that is a big opportunity for employment. So add to that recent IEEE survey that estimated that about 50% of the current workforce in power engineering, utility equipment manufacturers, so 50% of the workforce is at least eligible to retire. Whether or not they'll retire, hopefully they don't. But they're eligible to retire, which means they need to be, that expertise has to be somehow replaced, new workforce needed. Unlike some other fields, for example, computers, the power engineering work cannot be just shipped overseas. It is something that has to be done here. First of all, it's the physical infrastructure. That is one big reason. The other reason is the threat of the cyber threat, cyber security issues. Again, this cannot be just simply done overseas. So which means there's going to be a huge need. There's already a huge need for well-trained, US-trained engineers, and that is something that we are addressing through our undergraduate and graduate program. Okay, so the main focus for today's talk is on the courses that we offer. So this is the complete list of our undergraduate courses. 360 is the pathway course, so almost every other course has 360 as the prerequisite. So 4-credit course with a lab. So the lab has things on electric machines, a lot of power flow simulations, and a couple of experiments on power electronics. Okay, I'll go through each of these courses separately. Just wanted to mention that all of these courses, with the exception of 473 on machines, they are also offered online, and on-campus students can also take it through as a hybrid course. So this is a course that you would, if you take it as if you enroll as a hybrid student, you'll just be watching the recorded videos, just like online students. But you can attend the office hours and you take the exams on campus. And of course 488, 489 is the senior design project. Okay, so one unique thing for ASU Power program is we offer this concentration in electric power and energy systems. So if you opt for this concentration, your degree would be Bachelor of Science in Electrical Engineering with a concentration in electric power and energy systems. It's becoming popular, I would say. The enrollment keeps increasing. The requirements for the concentration are, of course, 360, that's a pathway course, and then at least 3 courses, 9 hours of the power area courses, the things that I showed in the previous slide. And also, you can also take courses, some of the 498 special topics courses related to power engineering or photovoltaics, as shown in this example. And the other major requirement is your senior design project has to be in the power area, advised by one of the 15 power area faculty that I showed. What counts as power area senior design project is decided by the chair for undergraduate studies. So I would say the power area faculty have been fairly active in advising senior design projects. My team last semester and this semester, they are working on a smart PV inverter, advanced PV inverter. Right? So PV inverters, as I'm sure aware, they convert the DC power from the PV panels to AC and then feed it to the grid. So what the smart inverter would do is will do much more than that basic functionality. It will also interact with the utility grid and do a power factor correction or reactive power support, do voltage regulation. A lot more advanced functions than simple DC to AC conversion. So that's something that the senior design project that team that I'm advising, they are working on. Okay, so the overall power engineering discipline can be classified into 3 major subdivisions. So you'll see that our courses are also arranged to cover each of these 3 areas. So those 3 areas are generation, how we generate electricity from various energy resources, and then how do you transmit and deliver that to the load centers, and the last one is how do you utilize that electric energy. So the power generation, as the name suggests, covers all the power generating plants from different fossil fuel based as well as renewable based resources, and then power markets is also considered as part of power generation, because how do you optimize which generator to be fired on during a given time is related to the economics and power markets. So that is usually considered as part of power generation. The second one is probably the bulk of what a power system engineer would be doing on a daily basis, designing different T&D infrastructures. Okay. So this is related to you generate the power using the generators. How do you transmit that to the load centers through this thousands of miles of transmission network and even larger distribution network. The last one, okay, I think I have something related to that. Okay. Right, so this includes power systems analysis. We have several courses talking about that. Then the power system protection using both conventional circuit breakers and so on, as well as the emerging power electronic based protection. The last one is utilization. So this covers electric motors and then all the power electronic devices. So there is a recent survey that showed that presently more than about 60% of all the loads are powered by some sort of a power converter. Okay, so you know that all your electronic equipment, from cell tops to large mainframe computers to TVs, everything is powered by a power electronics power supplies, large electric motors and so on. So more than 60% of all the power that we use is processed by a power converter. Okay, so this is not just the main utility power systems that has these subsystems. Large aircrafts, large ships, they also have the big power systems. They also have these three major subsystems: generation, how to transmit within the aircraft or within the ship, and then the end use. So if you're an expert in electric utility power systems, then you're also an expert in the other areas that I showed. So the next several slides talks about these three areas. One kind of introductory slide on that subsystem, and then talk about the courses, undergraduate courses that we cover within that subsystem. So we'll talk with the generation. I'll start with the generation first. I chose to put completely renewable energy related generation because that is the kind of the hot area recently. So utility scale renewable energy is mostly solar and wind. Solar can be either PV based or solar thermal, using these mirrors and generate electricity by rotating a machine from the power generated from this. Wind onshore or offshore, this is an offshore wind plant, and except for concentrated solar, whether it is a solar PV or a wind generator, they have to be necessarily interfaced to the grid by a power converter. So this is your example topology of a power converter for a wind energy system. Okay, so in this area, the courses that we offer, actually each subsystem has two courses. So here we have the basic course 463 electric power plants. So as you can see, it covers power generation using coal, natural gas, nuclear, and the renewables. So the hydroelectric plants is also normally clubbed under the renewable category. So that is a big part. Then increasingly solar and wind. Okay. So here we learn about how does each of these power plants operate, what are all the various issues, what their efficiencies are, and how they should be controlled, and some aspects of economics, power system operation is also included under that. Recently, we have also added topics on energy storage in this course. 460 taught by Professor Holbert on nuclear power engineering. So here also you have just a brief overview of nuclear power generation, but this course is completely about nuclear power generation, starting with the physics, radioactivity, and so on, to the design of nuclear reactors and power plants using them. Okay, then moving on to T&D. So this slide shows, gives an idea that it's not all theory. If you make a mistake in design, it has huge implications, almost life and death implications. So this is a cover page from Time magazine when the 2003 major blackout happened. Luckily, since then, not major blackout on that scale has happened, but blackouts are becoming kind of more frequent occurrences for several reasons, but not as major as the one that I showed. The main point is there is a lot of practical things, which is what makes this, at least to me, to several others, quite exciting field to work in. So why is this related to the T&D section? Because by better design of our transmission, distribution, providing more intelligence in the way these are operated, we can prevent or at least localize some of the large blackouts. Right? So I don't know if this could have been prevented, but if we had the advanced tools and advanced tools that we have now, we could have at least localized. This was something that covered the entire Northeast and also large parts of Canada. So we could have localized this to just one utility if we had. They blamed this completely on lack of situational awareness. Okay. So if we had that sensory information, we could have made this a much smaller event. Okay, so under T&D, the courses that we offer are 470 electric power devices. This is on protection of large transmission system. For some of you, maybe the term power devices mean completely different. For power electronics people like me, it means power devices or semiconductor devices like IGBTs and MOSFETs. So this course is not about that. Okay? This is about electric power devices, circuit breakers, relays, and zones of protection, and so on. Then 471 power system analysis is the staple of power systems engineers. So if you're not doing the concentration, if you want to do just one course in power systems in this area, then probably this would be the course. If you want to specialize in the power systems area, if you want to focus more on the power electronics part, then that will be 472. Okay? But this is one of the most important courses if you want to work in this area. Okay? So this covers mostly different methods for power flow analysis. So you know that we have extremely large transmission system, thousands of miles of transmission lines. So this calculates what is the power flowing, what is the current flowing in all of those transmission lines, what is the voltage at those thousands of buses, given some information on the load and some information on the generation. Yes. Okay, then the third area, which is the utilization. Here again I show a lot of power electronics applications and a lot of motor drive applications, because that is the emerging trend. Right? So a lot of penetration of power electronic converters in almost all aspects of the power systems. In the generation aspect, renewable generation, as I mentioned, solar and wind, they are interfaced necessarily through a power converter. In the T&D area, some application in the transmission is called as flexible AC transmission system, FACS devices. That's a power converter that controls the power flow. Then the utilization, as I mentioned, 60% of your power is processed by a power converter. So some examples of how the adjustable speed motors in washers and dryers, in refrigerators, can make the system more energy efficient. It also gives you more functionalities and more flexibility. So one big area that emerging market for is the electrification of transportation. I was doing some other paper for which I saw that last year in the US we sold more than 200,000 electrified vehicles. That includes pure electric vehicle as well as plug-in hybrid electric vehicle. So that's not a negligible number. It's still, overall sales is about 10 to 12 million. So compared to that, it is still very small. But 200,000 is it's not something that you can completely neglect. Okay. So what does that mean for power systems, power electronics engineers? There's a lot of power electronics inside a car. The main drivetrain, the motor that runs the wheels, that is driven by a power converter. Right? The batteries, they need to be charged, so that is the power electronics. For power systems, it has impact because it's going to be powered from the grid. Right? So if it is less than 0.1% penetration, it's not a big deal. But as it becomes more and more, like 3%, 5% penetration, then it becomes significant. Right? How do you, first of all, it's increased load. So you have to make sure that you charge when there is lower demand and so on. Okay, so the courses that we offer in this area is 472 Power Electronics. This is the basic power electronics course. Here we learn about the different circuit topologies, buck converters, boost converters, and so on, isolated topologies, as well as introduction to applications in renewable interface and recently electric vehicle power converters. I teach that course. 473 Electrical Machinery. This talks about all the 4 major types of electric motors, DC motors, then the brushless DC, induction machines, and synchronous motors. It also has a few lectures on the transformers. Some other universities have multiple courses on electrical machinery, but here we have just one course that covers all the 4 major types of machines. Okay, so this is getting a little bit into the research aspects. Let me stop here briefly and ask if there are any questions on the courses or anything else. Yeah.
Regarding the course AE 470 in the study of circuit breakers, I've been told that there's starting to be a switch from the actual physical circuit breaker, and it's actually starting to be like run through mainframes to tell when to actually break a switch. Do you guys study that at all?
Yes, yeah, that is the main focus of these. So the focus is on power system protection.
Okay.
So here it talks about so there's a fault, what are the fault currents? So how do you estimate a fault current? So it covers that. Then it talks about how do you divide the complete, say the US is divided into 3 power area networks. So the one that we belong to is WECC, so Western Electric Coordinating System. So the WEC system, how that is broken into various zones of protection. So that we learned that. And then we get into the devices, the circuit breakers and the relays mostly. So how to design them, how to set the ratings of these devices, and how do you have this the settings for the relays, right? This coordination. So you don't want a circuit breaker to unnecessarily open and take out large parts of the grid. So those are things that we learned in that course. So what I meant is not covering the semiconductor devices is power devices to people outside of power means it is IGBTs and MOSFETs and so on. So that is not something that we cover in this course. We do a little bit of that in 472 because power converters that makes use of these IGBTs and MOSFETs. Any other questions? Yeah.
You mentioned the concentration in electric power and energy systems.
Yes.
Moving forward into employment, is there a notable advantage to having that concentration on your degree versus just having a BSc in electrical engineering?
Very much so. So it gives a stamp that you are specializing in the power area, right? And the fact that even though there is only 3 course minimum requirement, most students who take this concentration end up doing 4, more often 5 courses in this area. So you do become an expert, and then it is a major point in your resume if you are focusing on a career in power area. Yes, it is a big help. Yeah. That is one of the primary motivation to offer that. Yeah.
You also stated that you expect a 50% increase or a 50% utility workforce will retire in 10 years. Do you expect a greater increase in like the need for them too, as how much work would be needed due to cities realizing that their utility lines are
yeah, exactly. Exactly. So it's twofold. One is there is a need for more infrastructure to be developed, so there is more work, but less workforce, trained workforce. So that means much bigger opportunities for new graduates.
Okay.
Yeah.
Just wanted to go back to the gentleman who asked about the concentration.
Right.
It doesn't appear on your diploma. It appears on your transcript as a stamped concentration. So you can distinguish yourself as a BSc in electrical, and then show them and provide that additional documentation. Just so you know. Just want to clarify.
Okay. All right. Yeah. So we have an award called Gurur Family Award. Dr. Gurur was a former faculty in the Power Group. He is now going to University of Alabama as a department chair. So this award is named after him, and this is meant for the top graduating student in the power concentration each year gets that cash award. All right.
I have a question.
Yeah.
If we're interested in the PCERC stuff, are there, of the three, is there one specifically or two specifically that we should emphasize with these classes?
Yes, the 471 is what much of the PCERC projects they relate. I mean, this is still an undergraduate course, right? PCERC is mostly MS, PhD level research, but this will be the background course, and then you'll certainly need to take some of the more advanced graduate level courses to be able to do the projects that is typically conducted under PCERC. They do not have as many projects in the power electronics area as they do have in more traditional power systems. So that is why I mentioned 471 rather than 472 or others. Okay, so there are just two main themes that I want to emphasize as part of research. One is I call this a paradigm shift. So the current paradigm or recent past paradigm is you generate electricity in these huge power plants, often coal and nuclear power plants, far away from the load centers. Then you have these extensive transmission distribution network, bring the power, and then they are finally consumed at the residences, industries, and commercial places. The paradigm shift is you generate electricity locally through mostly renewable generation, which doesn't have to be any distributed generation. So rooftop PV, smaller scale utility power plants, like these are like 1 megawatt power plant, PV power plants located right inside the distribution system. Probably they are located in a substation. Then you have 100 kilowatt level commercial PV plants like Walmart and other places. They have fairly larger scale than your residential PV. So the paradigm shift is that it's no longer power generated remotely by just a few utilities. It is ubiquitous generation. Almost every homeowner is now, they have a different word. It's called as a prosumer. It's not a consumer, it's a prosumer, meaning they both produce power and consume power. So why is it a paradigm change? Is because everything has to be redesigned if the distributed generation percentage becomes much higher than say 20%, 30%. We mentioned protection, right? So protection has been designed based on the philosophy that power flow is always from substation to the load. Okay? Now if you have PV on every rooftop, power flow is going to can be in the opposite direction, and the protection systems are not really designed to handle that. Okay? Right now we are getting along because the penetration level is not that high, but even now there are pockets where it is already a problem. Okay? So that is one big thing. The second one is managing these using more sensory information that leads into smart grid and so on. The third one is all of these generators are necessarily powered by a power converter. Right? So as a power electronics person, I feel very good about my job security, right? So it's a lot of power electronics and everything related to power systems. So that's one big area. The second one is smart grid. Okay? So if you're here attending a power systems seminar, then I would assume that you've at least heard of the term smart grid. So this is, in a nutshell, this is the confluence of your power systems network and a communications network. So this is, these are the various components that make up a smart grid. So I already talked about renewable generation. This is rooftop PV. Then a big part of that is advanced metering. So it's called AMI, Advanced Metering Infrastructure. So even now, you can just log into your APS or SRP account, and you can see your energy consumption on an hourly basis throughout a year or yesterday or whatever you want to see. Utilities gather this information even on a finer scale. Right? I think they can get every second information. So you have this huge amount of information available, and there's a lot that you can do with that information, and they're just beginning to make use of that. So for example, earlier, if there is a power outage, they have to wait for the customer to call them to say that my power is lost. But now they can, within a second, they know that the power is lost to that customer, and they can do some corrective action. There's one very small, minor example. There's a lot more that you can do. Plug-in hybrids, a lot and more. Like I mentioned, 200,000 cars. They are plugging into the utility grid. So that is both a problem to be solved as well as an opportunity. It's an opportunity because it represents huge amount of storage. Right? These electric vehicles have batteries. Those storage, when they are not running on the roads, they are plugged into the grid. They can be used to, have a better load profile, use it as a storage. So earlier, even the little information that they had was only restricted to large transmission system, but now they are getting into distribution all the way to your individual residence and see what is happening to the electric grid at that fine level. So this is another area that almost each of the 15 faculty that I showed are working on different aspects of smart grid. Okay, so we are also part of some major centers. So somebody mentioned PCERC. We are the lead school in PCERC. It's a consortium of 13 universities and about 40 to 50 industries, mostly utilities, ISOs, independent system operators, and then large electrical equipment manufacturers like ABB, Siemens, and so on. So many of our research projects are funded through PCERC. And as I mentioned, it is heavily focused on power systems. They have different stems on markets, T&D and general power systems, not that much on power electronics. Professor Vittal is the director of the overall center, and the AAC site itself, Professor Haidt used to be the site director. Now I think after he's retiring, it's taken up by Professor Hedman. We are part of another smart grid initiative center called Freedom Center. It is led by NC State University. ASU is one of the big partner universities. So here is the focus is on power electronics for smart grid. It's a 10-year program, and actually we are on the 10th year. We'll get one more year extension, but the center is actually winding down. Quest is probably you're familiar with Quest. This is an ASU-led NSF ERC focusing on the solar PV, semiconductor physics mostly, but there is some aspect of that is related to power systems and power converters. These ERCs, these NSF centers, they emphasize a lot on undergraduate research, so there may be opportunities for undergraduate research as part of the Quest Center as well as the Freedom Center. Okay, another big center, this is 70 million DOE plus another 70 million industry supported center, again led by NC State. ASU is one of the 10 universities in that center. So this is a completely power electronics focused center. There is new type of material for power devices called wide bandgap semiconductor materials, gallium nitride and silicon carbide. So they call that as a revolution in power electronics, because the advantages of these material is so striking compared to silicon that the efficiencies can go directly from like 90% to 99% efficiency using these devices. So our focus in this center is using these materials to build more efficient and more compact power electronic converters. The last one, geared, is more of an educational training center led by EPRI, and ASU is part of that. Okay, I think this is the last slide. So we have several power systems laboratories. We have 2 high voltage labs led by Professor Karadi. We have a power electronics lab. This is a picture of the power electronics lab. Then we have electronic controls of power systems lab. Again, it is Dr. Karadi's lab. We have a power system simulation lab. So almost all the full industry grade software that you would need for any type of power systems analysis, we have that full industry grade, not just educational licenses. So that is the lab in the ERC. Then we have instrumentation lab, Dr. Holbert's lab, and some fiber optic cable testing lab also. Okay, I think that is all that I had. Open to questions.
I had a question.
Yes.
More about the PSERC. I've been interested in it, but how big is it with industry? Like, is there a huge demand for that sort of research? Is it just kind of a small little niche right now? I'm just kind of curious of the scale of how much it translates into the industry.
Okay. Yeah, so this, the unique thing about PSERC is it's completely industry driven. Unlike, for example, the Freedom or the Quest. So it's a 10-year program, so we write a proposal saying that during these 10 years this is what we'll be doing. Right? And then at the end of the 10 years we need to deliver that. But PSERC operates completely differently. So all these projects are suggested by the industry. So they actually come up with the topics, and then the professors write proposals based on those topics. So you will see that all the projects are completely industry relevant. We publish based on that research, but it's more industry focused, based on their immediate needs or their expected forecasted future needs. So it's that's the unique thing about PSERC. And I mentioned about 40 to 50 industries. So they come up with these research topics, and then we try to solve some of the challenges that they are facing. So EPRI is the alternate research organization which does that kind of work, but we also kind of do a little bit more, I would say, advanced, more theoretical work, but relevant to industry needs compared to what EPRI does. In fact, EPRI is also part of PSERC, as are some of the other ISOs which do research in-house also.
Which one is part of it?
The California ISO, Independent System Operators. They are some of the major employers of our students. Any other questions?
If we wanted to know more, based off of, you gave us descriptions of the faculties, can we just email them if we have more questions, or if we want to ask?
Yes, certainly. So the emails are there on the department website. Yes. All right. So thanks everyone for coming. And
Thank you, Dr. Ayyanar.
thank you. Thank you.